Hey everyone, welcome back, and let's write some more neat code today. So today let's solve binary tree maximum path sum. And yes, this is another problem from the blind 75 LeetCode list. So this is a list of 75 common LeetCode questions, and today we're going to be solving this tree question, binary tree maximum path sum. The link to this spreadsheet will be in the description if you do want to take a look. And I think I've almost done all of the problems that I wanted to do. from this list, nearly all of them so far. So a path is defined in a binary tree as being a sequence of nodes where each pair of adjacent nodes in the sequence has a edge connecting them, and a node can only appear in the sequence at most once, and the path sum of that path is defined as being the sum of all the nodes' values in that path. So for example, in this example, we're given a tree, and the path is basically going like this, right? You see nodes, right? So then what would be the maximum path? I think, well, what if we have a tree of all positive values like this one? Can we just take every single node, like basically like this, and call it a path and just add every value together? Well, no. And the reason is because if we had this structure, right, this isn't really a path, because how would you traverse it, right? We could start here from the left side, choose the bigger one, that's a 5. Right, so take a look. What would the sum be if we ended up splitting from here? This is obviously the max we could create. What is the total? It's 1 plus 2 plus 3 plus 5, which is going to be 11. Now, we're going to try it multiple ways, right? It's possible maybe there could be a split over here. Of course, this doesn't have any children, so the most we could get doing that would just be a 2. But what about over here? What if we ended up splitting from here? So we took the left and the right from here. We'd get a 4 and we'd get a 5. Now, if we did do that, notice how this is going to be the topmost node. So whenever we split from a node, we can't really get any of its parents or anything like that. So in this case, what is the sum of this path? Well, it's going to be 4 plus 3 plus 5, which is going to give us 12. 12 is greater than the 11 that we had previously, so this is going to be the max path sum. So you can tell that a brute force approach would be for every single node, consider it being the topmost node, and then from the left subtree basically find what's the maximum path we could create in the left subtree if we never split. So we can't include both left and right, and then do the same for the right side, right? And if we sort of do it recursively, we can eliminate repeated work. So suppose we're given that same tree. We're going to start at the root like normal, right? So from here we want to know what's the max path sum we could do from here if we split from this position, right, going left and right. Now, why start at the root when we could solve the subproblem first and possibly use that subproblem in the result at the root position? So we're going to leverage that idea, a depth first search idea, just like usual with tree problems. And using that, we're going to end up getting a linear time solution, and it's just going to depend on the return value of our recursive function. So we're going to start at the root. And now we're going to go left, right? We want to know what's the maximum path we can get from the left subtree if we never end up splitting. So in this case, it's pretty simple because it doesn't have a left child or a right child, right? So we don't even end up having to split, and we get a sum of 2 from this spot, right? And even if we were splitting from here, we would get a total of 2 so far. So what we'll say is, so far the max path we've gotten so far is 2, right? Now, we still want to know what's the max we can get from this position, so what we're going to do is now go to the right tree. So recursively, now we're going to ask the question down here. What's the max path sum we can get if we ran it through this position and we ended up splitting left and right? And by the way, our result so far is going to be 2. That's the maximum path so far that we've gotten. So from here, we're going to, since we're trying to, again, find what's the max we can get splitting from here, we're going to go recursive, and we're going to do that for the left subtree and the right subtree. So we're getting that same base case here, right? With this left subtree, if we tried to split from here, the max path we'd get is 4 because it doesn't even have any children, right? So let's keep track of that. The max path we could get from here is 4. Now, if we didn't split here, we'd also get that same value of 4. And that's what I'm marking here. Next to each node, I'm marking what's the max we could have gotten if we did not split. I know it's a little confusing, and it'll make more sense once I actually finish the rest of this example. And so from over here, now we do have what's the max we'd get from the left path without splitting. It's 4, but now we just want to do that for the right side. Once again, it's that same base case, right? So What's the max we could get running through here if we never split? It would be 5. It doesn't have any children, so we couldn't split even if we wanted to. So now we're at this node once again. We have computed the left and right subproblems. Now from this node, we're going to be computing split up here. We don't want to split. For this node, when we're returning up to our parent, is what's the max I could get than our result, right? So we actually don't update the result. We're up here, what we would end up computing is 3 plus -4, which is going to give us -1, right? -1. So what we would say is, okay, the max we could get here without splitting is going to be -1. But that's not actually the case, right? Because to get the maximum path sum from here where we're not allowed to split, it doesn't necessarily mean we have to include the children, right? They're optional. We could actually choose to not include either of these, and that's what we would want to do because they're both negative anyway. Why would we want to include some negative numbers? So when we're actually taking the max of the two, we're actually going to take the max of 3 values. We're going to take the max of the left, right, and potentially 0, because if we just add 0 to it, this will stay the same. So those are the key ideas I wanted to go over. I think that is enough for us to dive into the code to solve this optimally. So like I said, we're going to have a global variable for the result, and initially we're just going to set that to the whatever value happens to be at the root. So the reason I'm making it a list is because that'll make it so that we can modify it within the recursive function a little bit easier. So we're going to have a recursive DFS. We're going to pass in whatever root node we're traversing, and that's really all we have to pass in. So now the base case is that if we don't have a root, like if the node is null, in that case, what we're going to return is just 0. That means we're not going to be adding anything. And so we're going to be returning, I just added a comment, we're going to return from this function the max path sum without splitting. So we want to get the max path sum. So of course we have to do this recursively. So let's get the left max, and we can do that recursively. Just pass in root.left. If it's null, of course, that's just going to return 0. We're also going to get the right max, passing in root.right. So the first thing I'm going to do is compute the max path sum with a split from this root node. So basically what I'm going to do is I'm going to take the root.value and add it with the left max and the right max, right? Because we are splitting from this root node. Now, of course, these left and right maxes could be negative. So what I'm actually going to do before that is update them. So we're going to set left max equal to the max of itself and 0. And do the exact same thing with the right max. So it's going to be set to the max of itself plus 0. So here we're going to be computing the max path running through here. So we're going to take the root value, the left max, and the right max, add them together. Now this could potentially be our new result. So let's see if it actually is. So result at position 0 is going to be set to the max of itself, or this value that we just computed. So this is the part where we're actually computing what could actually be the updated result. Now, what the return value, remember, of this function is not going to be the same as this. The return value is going to be what we compute without splitting. So the return value is going to be return root.val plus whatever the max of the left max and right max is, right? Because we can't choose both, because if we choose both, that means that we're splitting. And so that's actually the entire function, right? You can see when we handle the recursive case well, and we take the max of it and 0, then we really just have two main computations we're doing, right? The max path sum with a split and the max path sum without a split. Of course, this one is going to be the return value. And after we're done with that, all we do is call our DFS, passing in the root, and then that will update our global variable up above, which is the result. Then we can go ahead and return that result, and that is the entire function. I'll run it, and you can see that it does work. Now, you might think it's a little bit cheating to even have a global variable like this, and it's actually possible to solve this problem pretty easily without a global variable too. I just didn't show it. The main way you would do it is, instead of computing this and updating a global variable, what we could do is we could basically return two values from this function. So we would return the max path sum with a split and the max path sum without a split. So I hope that this was helpful. If it was,
Okay, now let's look at graphs. We're going to start out by bringing this up. This is called a vertex or a node. The proper way to say it is vertex, but you'll hear the word node. And we'll bring up another vertex. The plural would be vertices. Then between the vertices, we have what is called an edge or a connection. The proper way to say it is edge. So we have vertices and edges. Let's bring in another vertex like this. So this vertex can have an edge with this vertex, or it can have one with this one, or it can have one with both. There is no limit to how many other vertices that a vertex can connect to. So now that we have a small graph, let's look at a couple of concepts. Let's say you want to go from this vertex to this vertex. Well, when you look at this, you would say that you don't want to go this way because that is 2 hops and this one is 1. You'd want to go the more direct route. But with graphs, one of the things you can have, you're not always going to have, but you can have, are weighted edges. So where you would use something like this would be in a Maps app. You're using Google Maps and the road between 76 and 82 has a lot of traffic, so you go this way instead, because this has a cost of 5 and going this way has a cost of 15. Another place you'll see something like this is with network routing protocols. It would be better to have an extra router hop and have 2 very fast links than to go the way with a very slow link. And like I said, the edges can be weighted or not weighted. So another concept with graphs. We'll explain this with a Facebook connection between you and a friend. So with a typical Facebook account, your friend is friends with you and you are friends with your friend. It is a bidirectional relationship. So in a graph where all of the edges are bidirectional, you'll often see it like this without arrows. And when you see it like this, it is assumed that it goes both ways. So let's compare this to something like Instagram or Twitter when you follow a celebrity. You are following the celebrity, they don't follow you back. That is directional. So the edges can be weighted or non-weighted. They can be directional or bidirectional. Also, we have seen a graph in this course. It was a tree. Trees are a form of graphs, but they have the limitation that each node can only point to 2 other nodes. And when we looked at trees, we had mentioned that we had seen a tree before, which was a linked list. So linked lists are a form of a tree, and a tree is a form of a graph. Therefore, a linked list is a form of a graph, with the limitation that they can only point to 1 other node. But we typically think of something that looks like this when we think of graphs. So there are 2 ways we're going to look at being able to represent a graph. The first one is going to be an adjacency matrix. The other one will be an adjacency list. So let's bring up a graph and we're going to represent this in an adjacency matrix. So we'll start by looking at this A vertex. It has 2 edges with E and B. So we'll say A has edges with B and E. And we'll just put 1s in those boxes there. And of course, A cannot have an edge with itself, so we'll put a 0 in that one. And then it does not have an edge with C and D, so we'll put 0s in there. Now let's look at B. It has edges with A and C, so B has edges with A and C, and the rest will be 0s. So I'll just finish building this out like this. to complete our matrix. So this axis represents the actual vertex. This axis is the items it has an edge with. So now one of the things that's interesting about an adjacency matrix, we had mentioned that A can't point to A, well also B can't point to B, and so on. You're always going to have this 45-degree line of zeros. And if you have a bidirectional matrix like we have here, you will always have a mirror image on each side of this 45-degree line that looks like that. But this is only if these are bidirectional. So let's change one of these to directional and take a look at that. We have a connection between A and B. So in the matrix, that is A connects to B, that's 1. B connects back to A, that has a 1. But if we remove the edge that points from B to A, and we change this to a 0, now we have lost our symmetry across that 45-degree line. So let's change the edge on the graph back to being bidirectional, and then we'll change it in the matrix, and now it is symmetrical. So another thing that you can have with your edges is that they can be weighted. So if they're weighted in an adjacency matrix, we will just store these weights in the matrix like this instead of having ones. Okay, let's put that back. And that is our quick overview of an adjacency matrix. So now let's look at creating an adjacency list. That's just going to be a different way of representing this graph that we just looked at in the last video. And with an adjacency list, we're going to represent this with a dictionary. Let's start with our A vertex. It has edges with B and E, and we'll represent this in our dictionary like this. A is the key, and we'll have a list for the value in our key value pair in the dictionary, and that list will hold all of the edges that A has with other vertices. So now let's start moving around this circle here. So we'll look at B. It has edges with A and C. C has edges with B and D. D has edges with C and E. And then finally, E has edges with A and D. So now this adjacency list on the right represents the picture on the left. And an adjacency list is what we're going to use to create our graphs in this course. And that is our overview of an adjacency list. Now let's look at graph big O. So I'm going to bring up the same graph that we've used in the last couple of videos here, and we're going to represent this graph with an adjacency matrix and also an adjacency.
please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.
Hi, I'm Dan Weston from Confluent. In this video, we'll take a look at the Kafka consumer and the things you should keep in mind as you build your Kafka cluster. There are three main pieces to a Kafka-based architecture: the producer, or where messages come from, the Kafka cluster itself, and the consumers. To understand consumers, it's helpful to follow the message path as it moves through your Kafka cluster. Messages can be any event. A sale was made on your website, a temperature sensor recorded the current temperature, or an order was shipped. Each of these messages contains 5 core elements and one that's optional: the key, the value, the timestamp of when the message was created, the current message offset, the partition that the message comes from, and the optional headers. If message order is important for your application, you'll want to provide the key. This ensures that messages are sent to the same partition and kept in the order that they were received. The key is also used to serialize the message before being sent to Kafka and deserialized in the consumer. Consumers subscribe to your topics and pull from messages. One of the things that sets Kafka apart from other messaging systems is that once a message has been consumed, it is not deleted. Instead, each message stays around until the retention period is met. This is one of the main reasons why Kafka scales so easily. You can have any number of consumers connecting to each topic. One of consumers' most important and often misunderstood aspects is understanding offsets. An offset is a unique identifier of a message in a partition. It's an increasing number that's assigned to each message when it is stored. Consumers can save which messages have been processed in a special Kafka topic that allows them to pick up where they left off in case something goes wrong. This operation is called committing offsets. By default, the Kafka Java consumer does this automatically for you and offers at least once delivery. If you aren't going to be using the Java consumer, you'll want to check out the default behavior of your selected language. For an example of how .NET implements consumer offset, be sure to check out our course, Apache Kafka for .NET Developers. Each consumer is part of a consumer group. Each group can be as small as one consumer or as large as the number of partitions in your Kafka topic. Each consumer in a group adds parallelization for that task, splitting the messages among the consumers. For example, let's say you have a topic that has 1,000 messages arriving per second. If your consumer can only process 500 messages per second, you would never catch up and you'd eventually fall significantly behind. However, if you added another consumer to that group, you'd be able to handle all 1,000 messages per second. Kafka automatically assigns consumers to partitions within a consumer group. So, if you had one partition, you'd be able to have one consumer. If you had 3 partitions, you'd be able to have 3 consumers. For instances where you have less than the maximum number of consumers, Kafka will assign consumers equally. So if you had 5 partitions and only 4 consumers, each partition would be assigned to a consumer, with one consumer being assigned to 2 partitions. This is the same thing that happens when you have a consumer that fails or is added. A rebalancing takes place and assigns partitions to consumers. If you need additional consumers in a group, you will also need to add more partitions to your topic. It is also common to have a consumer act as a producer. In this scenario, you would have the application consume the messages, perform any analysis, aggregation, or other transformation, and then send it back to the separate Kafka topic. Now that we have a better picture of how a consumer works, let's take a look at a simplified consumer configuration. This is a sample configuration taken directly from Confluent Cloud. First, we provide the properties, like the Bootstrap server and any certificates or API keys to connect to our Kafka cluster. Next, we provide the group ID for our consumers. Third, we set the offset behavior. This property can contain 3 options: earliest, latest, or none. If you care about all of the messages in a topic, you should select earliest. If you only want to see the messages from when your consumer connects onward, select latest. None will throw an exception if there is no offset for the Kafka cluster to check for new messages, and then we print the key and value of our message. That's the basic of Kafka consumers. Let us